Hello, you. Today we're gonna make a brief introduction about porous media flow. Let me introduce my teammates first. They are Diana, Maximus, and Harsh. Our presentation will be separated into four main parts. So the first one is introduction, the second one is modeling methods, and the last one is challenges. So first, in class, we learned how to calculate void volume in materials and estimate the time. However, real-world cases are more complex and require us to develop more precise models to predict their behavior. First, let's briefly review what we learned in class. You can see that Darcy's law discovered fundamental for understanding fluid flow through porous media. Originally derived from experiments observing water flow through gravel, it was later found in many fields, including hydrology and engineering. That said, Darcy's law has its limitations. It is invalid for non-Newtonian at high velocities and gases at extremely low or high velocities. The generalized Darcy equation, however, has been widely used during geological carbon dioxide storage and biochemistry we will discuss later. In 1901, an empirical equation to describe nonlinear flow behavior. He observed that as flow rates increase, the derivation from Darcy's linear. For example, in hydraulic fractures, high fluid velocities induces significant inertial effects, which lead to production rates. To better understand these complex behaviors, we use mathematical models to predict flow in porous media. Simulation is one of the mechanisms governing flow through porous structures. Fluid flow in porous media strongly depends on the microstructure. Both pore size and topology significantly affected the relationship between the non-Darcy coefficient and other parameters. To address this, a fractal pore-through train model we call FPTCM has been proposed to structures. We can see that it's a little bit different from the samples we learned in class. The fluid flow paths within a representative volume element surrounded by bundles of pore-through chains. Each chain is composed of multiple interconnected pore-through structures with the same pore-through. There is how we got the fractal dimension, and then we use the fractal dimension to get the RAV, and then finally we can got the. After we making this assumption, we can use it to analyze the Darcy flow. For steady-state laminar flow of incompressible Newtonian fluid through porous media, it is assumed that the inner walls of the pore through conditions at the interface. So according to the Hagen-Poiseuille equation and conservation of mass, the flow rate through a throat and is equal, so that we can get the whole flow rate Q, and then we can use the Q to get the Darcy permeability. Theta is the solid fraction in the porous media. Consider the non-Darcy flow, which is different is that the high-speed fluid flow through pore-through structures resulted in localized energy loss. The local kinetic energy loss coefficient for sudden expansions and contractions in pore-through units. The total pressure loss combines loss per unit length and the local loss per unit length, so that we can get the total pressure loss, and using the total pressure loss, we can get the. It is very important that combine the model we assume and using simulation to get the results. We need to decide and apply the boundary and initial conditions and using computer to solve it, as we did in the class. Then we can get a better understanding. Now let's move on to an interesting application of these models in bone modeling. Bone is a function of forms, cortical bone and cancellous bone. You can see that there are blood, interstitial fluid in it, so we can cross a porous media. Considering the interactions between blood and bone tissue, we can extend the principles of Darcy's law and Forchheimer's theory to generate equations that fit these conditions. Darcy flow, and the right-hand side is the influence of Forchheimer flow. This allows us to better understand fluid flow and nutrient transport within bone structures and physiological processes. My teammate may use Python or MATLAB code to show how we can learn from this model in the future.
Hello class, my name is Maximus and today I'll be presenting the biomedical applications of porous media modeling. So in this paper by Kasari and Vafai, the aim is to explore blood flow interactions in porous tissues to enhance the understanding and application of porous media modeling in biological systems. Well, why do we care? Well, biological tissues such as organs and bones contain porous structures that transport nutrients and heat. So let's start off with a physical picture to so you can see what we're trying to model here. This illustration shows blood flow interactions within a porous medium. The vascular region shown in red represents the blood vessels which transport nutrients and fluids throughout the body. Surrounding these vessels are the extravascular region in blue, which acts as the porous medium. Within this region, the pores, or small spaces in the tissues, play a critical role in allowing movement and fluids and the movement of fluids and nutrients between blood vessels and surrounding tissues. To model blood flow interactions with porous tissues, we use mathematical models and equations that represent the physics of fluid movement through porous structure. These models connect biological systems like tissues with fluid mechanics and transport physics. So let's break down these key models. Darcy's law is important to modeling flow in porous media and applies to slow laminar flows where viscous forces dominate. In biological systems, Darcy's law helps us understand how blood flows through porous tissues, such as capillary networks. So just take a look at the equation. It's pretty simple. You can pause it and look at the parameters. So I want you to think of it like water flowing through a sponge. The flow rate depends on the porosity of the tissue and the pressure applied. Darcy's law pretty much captures this relationship accurately for tissues where Reynolds number are very low, typically less than 1. You can see this linear relationship clearly in the graph of flow velocity versus pressure gradient. So an extension of the Darcy's law is the Forchheimer's equation, which builds on the Darcy's law to account for nonlinear drag forces that arise when flow rates increase. This is pretty important for tissues with dense structures like muscles, for example, where flow resistance becomes pretty significant. So again, you can pause and take a look at the equation and the parameters. So as shown in this graph, Darcy's law predicts a pretty linear relationship between pressure gradient and flow velocity. However, the Forchheimer's model includes a steeper curve at higher velocities, pretty much reflecting the increased drag forces. This transition from linear to nonlinear behavior is captured pretty clearly in this graph. The Brinkman equation also extends Darcy's law by this time including a diffusion term. So just take a look at the mu del square V. Again, you can pause, take a look at the parameters. So it pretty much models viscous effects in highly porous tissues like spongy bone or marrow. So the graph on this slide pretty much shows how fluid velocity decreases with a distance over time due to diffusion effects. At longer distances, the impact of diffusion term becomes more and more apparent, slowing the flow and spreading it more evenly throughout the tissue. As the velocity profiles flatten out at greater distances, this pretty much shows the contribution of diffusion effects in highly porous media. As a result, the study validated these mathematical models through numerical simulations and also explored practical applications in biological systems. So, more specifically, they found that Darcy's law accurately predicts laminar flow at low Reynolds number. The Fortenheimer's equation models nonlinear drag forces in denser tissues with moderate flows, and the Brinkman equation incorporates diffusion effects in high porosity tissues. So, some key takeaways, right? In this slide, we see how specific models align with their respective biological applications. So, for example, the Darcy's law, it's ideal for low velocity laminar flows. It applies to blood perfusion in bone tissues, for example, where the flow is steady and proportional to the pressure gradient. The Fortenheimer's equation, it accounts for nonlinear resistance and is critical for capturing nutrient transport in denser tissues like muscle, where increased flow resistance comes into play. So finally, the Brinkman equation, it adds diffusion effects, which is essential for understanding flow dynamics in highly porous tissue like the spongy bone or marrow. So collectively, these models have been proven to be useful in biomedical applications such as drug delivery, wound healing, and thermal regulation.
Another example of applications of flow in porous media would be carbon dioxide sequestration. And to go into depth about this, we have a paper titled Pore Scale Modeling of Multi-Phase Reactive Flow Application to Mineral Dissolution with Production of CO2. And while the authors do not explicitly mention carbon dioxide sequestration, the processes studied, such as mineral dissolution, bubble formation, and the impact of flow dynamics, are directly relevant to carbon dioxide injection into saline aquifers, where similar reactions and multi-phase interactions occur. And we will go more into depth about this. Flow in porous media is crucial for processes like groundwater transport, oil recovery, and carbon dioxide sequestration. When carbon dioxide is injected into saline aquifers, it reacts with brine and minerals to form carbonic acid, which dissolves minerals like calcite. This process alters the rock's porosity and permeability. A critical challenge is that carbon dioxide bubbles produced during dissolution can change flow dynamics, potentially blocking pathways of reducing efficiency. Most prior studies focus on single-phase flow, but this paper addresses the need to model multi-phase system at the pore scale. A multi-phase flow model is essential to understanding the interactions in carbon dioxide storage systems. This study aims to develop a pore scale model that captures the behavior of carbon dioxide bubbles and their impact on dissolution processes. The authors developed a Darcy-Brinkman-Stokes, or what they call a DBS model, to simulate these complex systems. A Stokes flow governs regions without solid structure. Brinkman equation handles flow in porous media, accounting for both viscous and drag forces. And finally, Darcy's law describes flow dominated by resistance in highly porous regions. This unified approach bridges free fluid and porous flow regions, making it ideal for simulating the interaction of fluid phases in reactive systems such like carbon dioxide sequestration. The DBS model uses several fundamental equations. First, we have the conservation of mass, which ensures mass balance across fluid and solid phases. Secondly, we have the conservation of momentum, which includes viscous forces, drag forces, and surface tension. This model takes into account porosity, which is described by epsilon, and it's equal to the void volume divided by the total volume. And when epsilon is equal to 0, it means that the field region is fully fluid, and when epsilon is equal to 0, it means that it's a solid region. Incorporating porosity in the conservation of momentum equation will look something like the second equation in this slide. For this equation, we also take into account permeability, and we can see that for the first equation. In this slide, this represents permeability, and it takes into consideration a K0, which means a reference value for permeability, and also taking into account the porosity, which is epsilon. Also, we introduced terms like surface tension force, which is represented by Fc, and also takes into consideration the porosity, which is epsilon, a surface tension coefficient, a normal vector at the gas liquid interface, like we can see on the image to the right, and a new term, which is the liquid saturation. And this will give us the average momentum equation. And this average momentum equation is a modified version of the Navier-Stokes equation designed to describe how fluid flows through porous materials. It takes into account the space available for fluid to move, which is porosity, and the resistance caused by the porous structure, which is the drag force, and additional effects like surface tension. This equation is central to the model because it seamlessly transitions between free-flowing and porous regions, making it ideal for simulating CO2 movement and dissolution subsurface environment. To validate this mathematical model, the authors also conducted microfluidic experiments, where they set up they flowed an acid solution through microchannel containing a calcite crystal using high resolution imaging to capture CO2 bubble formation and crystal dissolution. What they observed was that initially small carbon dioxide bubbles formed uniformly at the crystal surface, and as they grew, these bubbles blocked dissolution sites, altering flow dynamics. The model accurately reproduced the observed patterns of bubble growth and dissolution, demonstrating its predictive power for pore scale phenomena. In summary, the authors developed a robust model for simulating multi-phase reactive flows at the pore scale, validated through experiments. This work provides critical insight into carbon dioxide sequestration by showing that CO2 bubbles influence dissolution dynamics and permeability changes. The DBS model bridges the gap between experimental observations and computational predictions, with applications extending beyond CO2 sequestration to groundwater flow and energy systems. This study underscores the importance of accounting for multi-phase interactions in reactive flow models.
Hello everyone. I will be presenting a study that focuses on the simulation of radionuclide transport in geological media using advanced mathematical modeling techniques. The study explores how radionuclides from a nuclear waste repository migrate through surrounding materials like soil, concrete, and sediment, and evaluates the effectiveness of these materials in preventing contamination. By using the Darcy-Brinkman equation and numerical methods, the research provides critical insights into designing safer repositories for long-term nuclear waste management.
This diagram illustrates the multi-barrier system used in nuclear waste repositories to isolate radioactive waste for thousands of years. The waste begins as small fuel pellets bundled into fuel rods and sealed in steel canisters, which are encased in copper overpack to prevent corrosion. A bentonite buffer, a swelling clay, surrounds the canister to limit groundwater flow. The entire system is buried 400 to 500 meters deep in stable bedrock, providing a geological barrier. This study focuses on how radionuclides might migrate through bentonite buffer and bedrock using the Darcy-Brinkman equation to model these processes.
This study models groundwater flow through the repository using conservation laws for mass and momentum. The repository is treated as a fixed domain with layers of soil, backfill, and sediment representing its physical structure. These layers allow us to simulate how water moves through the repository. The key equations ensure two things: mass conservation, that is, water flowing in matches water flowing out, preventing accumulation, and momentum conservation accounts for forces like pressure, permeability, and viscous effects using the Darcy-Brinkman equation. This forms the foundation for studying radionuclide transport. The next step is modeling how radionuclides like neptunium and uranium move through these layers. The equations include advection, that is how water flow carries radionuclides; dispersion, how radionuclides spread out influenced by molecular diffusion and flow direction; and decay, that is how radionuclides break down over time. The retardation coefficient captures how porous materials slow radionuclide movement by absorbing them. For uranium, the model also considers decay chains where uranium can form from neptunium's decay. These equations allow us to predict where radionuclides might accumulate and how long they could remain in the system.
To solve these complex equations efficiently, the study reformulates the transport equations into a Poisson equation. This reformulation simplifies the problem by turning it into a standard equation with a transport variable like radionuclide concentration and a source term that includes effects like advection, dispersion, and decay. The dual reciprocity boundary element method or DRBEM is then used to solve this reformulated equation. Instead of calculating everything across the entire domain, DRBEM focuses only on the boundaries, significantly reducing computational effort. It also uses Green's theorem to handle the boundary domain transformation. This numerical approach makes it possible to simulate radionuclide transport over long time frames and provides valuable insights into how the repository's material interact with these contaminants.
This slide outlines the simulation setup. The repository and surrounding layers, that is soil, concrete, and sediment, have distinct properties like porosity and permeability. Concrete, with its low permeability of 10 raised to minus 9 meters square, acts as a critical barrier. Initial radionuclide concentrations and boundary conditions such as seepage velocity at minus 0.25 meters per year are set to replicate realistic scenarios. These parameters form the basis for analyzing radionuclide behavior. In summary, this study emphasizes three key points. First, decay chains are crucial for understanding long-term radionuclide behavior. While neptunium-237 concentrations decline, uranium-233 concentration accumulates, particularly near the repository. Second, concrete acts as an effective barrier, significantly slowing down radionuclide migration due to its low permeability and high retardation properties. Third, hydrodynamic dispersion, including longitudinal and transverse effects, plays a major role in shaping radionuclide spread. These findings guide nuclear waste repository design, ensuring safety over thousands of years. They also support broader environmental risk assessment and groundwater protection efforts.
So these today. However, due to different limitations, we still need to define better models to use in real-life cases. In simulation and build mathematical real difficulties, such as complex rheological behavior, the surface smoothness of pores, the multiphase and multiscale effects, and predictions.